For part B, we're considering a different implementation of the priority queue. Instead of using a binary min heap, we're going to now use a hash map, okay? So with a hash map, what is going to be the runtime of a single call to each of these operations? Okay, so now we don't care about how many times we're calling each operation inside the entire Dijkstra algorithm. We're caring about, in a single call, what is the runtime using a hash map implementation? Okay, so remember enqueue is like inserting or adding something into our data structure. Okay, so what's the runtime for adding something to our hash map? It's constant, okay? What is the runtime for removing something from our hash map? Remember that we have to think about how we're removing things. So the Dijkstra algorithm is not just randomly removing any arbitrary vertex, it's removing the vertex that has the minimum shortest path length, right? So although removing any arbitrary vertex from our hash map is going to take constant time, removing the smallest length, smallest value in our case, right? Because our hash map is going to have keys as vertices, and then the value as the length of the shortest path. I'm going to abbreviate shortest path as SP. So in this case, right, we need to actually traverse all the key value pairs in our hash map, see which value is the smallest, which length is the smallest, and then delete that corresponding key value pair. So that's really just a linear traversal through our hash map. And so that is going to result in O of V time. Okay, so again, even though a single removal operation without having any specific criteria of what exactly we want to remove is going to take constant time in a hash map. In this case, in the context of the algorithm that we're caring about, we need to make sure that we're removing the min value key. Okay, is empty is going to check if our hash map is empty. That is actually going to be a constant operation. And the reason for that is because normally in a hash map implementation, you're going to keep track of a size attribute that denotes how many keys you have in your hash map. And so is empty is really just a matter of checking whether that size variable is equal to 0 or not. Contains key, okay, that is hopefully, you know that it's constant. And the reason for that is because, well, that's kind of what hash maps are for, right? You just hash into the hash map with the key that you want. And then if it has a corresponding value, then you know that it has that key in the hash map. Otherwise, you know that it doesn't have a key. Otherwise, you know that the hash map doesn't have that key. All right, and then the final operation is update. Okay, so update is also going to take constant time because we know the specific vertex we want to update, right? We're at a specific iteration of this for loop, and so we have access to this particular V. So really it's just a matter of indexing into our hash map. And by indexing, I mean really hashing. And then just getting the value of that vertex and then changing that value, putting it back in. Remember, putting it back in is constant. And so really is a total of constant time operation.